All right, so let's suppose we have an electric field, E, and let's say the components are 4x, that's the x component, I hat, and then minus 2 times x times y, j hat, and then let's say minus 7, k hat. And suppose we want to find delta V between, so find the change in potential between the origin, so that'd be 0, comma 0, comma 0, and some other point in the xy plane, let's say it's 3, comma 2, comma 0. Okay, and so if we were to draw this out, let's just draw the xy plane. Say there's x and there's y. So our first point is going to be here, the origin. Then our second point is going to be over 3 and then up 2, so maybe there. We're interested in finding the change in potential between those 2 points. Now, the great thing about the potential is that we can choose any path between these 2 points that we like. Now, you might think that a nice straight line path would be the simplest. However, that's not really the case. Instead of choosing that straight line path, what we're going to do is choose a path like this. We're going to go along the x-axis and then up on the y-axis. So that will be an easier path for us. So what we need to do is find the delta V for each of those paths. So let's say delta V1 is the delta V for that first path that goes along the x-axis. Now notice that in this case, ds is equal to dx times I hat, okay? So delta V, well, any delta V is always the negative of the integral of E dotted with ds. But notice that on this first path, since the ds vector is along the I hat component, or the x direction, that's just going to pick off for me this x component. So it's going to be 4x. So this is going to be negative the integral of 4x dx. And let's see, we're going to go from 0 up to 3, right? So that's over 3 and then up 2. And so this is an easy integral to do. And so delta V1 for path 1, let's see, this would be minus 2x squared, right, from 0 to 3. And so that would be negative 18. So I get negative 18 volts for path 1. So the potential difference between this point and this point is negative 18 volts. Okay, now let's do path 2. So this would be delta V2. And notice that for this path, my ds is going to be in the y direction. Right? So now my ds is dy times j hat. And when I do the dot product of my electric field with the ds, well, this time it's just going to pick off the j component, or the j hat component. Okay, so that's minus 2xy. So I get minus 2xy times dy. And let's think about y, right? Y is going from 0 to 2. Right? Y is going from 0 to 2 along path 2, which is over here. Now, the other thing to notice is that notice along this path, x is a constant at 3. So x shouldn't really be a variable. X should be a constant. Of course, the minus and the minus go away. And then 2 times x, that's going to be 6 times y dy. So when I integrate this up, this gives me 3y squared from 0 to 2, which is going to give me, let's see, that's going to give me 12. Okay, so your total delta V is simply the scalar sum of delta V1 and delta V2, right? I don't have to worry about components or anything. So I take my minus 18, take my minus 18 and my plus 12, and that gives me minus 6. So final answer here would be minus 6 volts. So the potential difference is negative 6 volts between the origin and this point up there. So in other words, this point up here is 6 volts lower than the origin. All right, so that's it.